All right, in this section, this is 2.4, we're going to talk about the graph of tangent. If you actually look at the book, it probably says the graph of tangent and cotangent. We're not going to do cotangent. It's super rare to even look at the cotangent. So we're just going to do tangent. 2.5, I believe, is the graphs of secant and cosecant. It's super rare to ever have to look at those graphs, so we're just going to actually skip that section. So the three trig functions that you really have to know the graphs of: sine, cosine, and tangent. Okay, so that said, the way we're going to figure out the graph of the tangent, we're going to do it in a couple ways, but one of the ways we're going to use analysis on whether tangent is even or odd. And so if you haven't watched the Math 92 lecture for this week, you probably want to right now and then come back to see this, because that's how we're going to get information about what tangent looks like. Okay, so let's start with analysis about the even and odd or oddness of tangent. So what I'm going to do is, first I'm going to start out with tangent of x. That's equal to sine of x over cosine of x, right? That's our definition of tangent, in fact, right? So if we want to analyze the graph of tangent, we can do that through analyzing sines and cosines. Okay, so what I'm going to do is I'm going to first show you that tangent is odd. So let's look at, so since we're looking at this right-hand side, we're looking at tangent as sine over cosine. I'm going to think of the picture, the original picture definition of sine and cosine, our picture definition of sine and cosine, right, with the unit circle. So this is radius 1. So if I look, let me label these in radians. So this is 0 radians, pi over 2, pi, 3 pi over 2. All right. So in effect, we're actually, let me think of this as minus pi over 2. All right. So that would be, again, we're going this way as opposed to counterclockwise, clockwise as opposed to counterclockwise. So in effect, what we're analyzing is the portion of the graph here, portion of the graph here. All right. And then let's do that first, and then we can kind of get some information. So what we have is between 0 and pi over 2, what is sine? Well, if I have any angle, just straight from the definition of sine and cosine, if I have any angle x, right, I'm looking at sine x over cosine x, then this point right there has coordinate cosine x comma sine x, literally the definition of sine and cosine, right? So what that means is that horizontal length right there is cosine x, and this vertical length here is sine x. All right. Okay. Let's compare. So this would be, for example, in terms of my graphing axis, maybe I'm looking at a point x right there, right, between 0 and pi over 2. So the question of whether tangent is odd or even is a question of what is the value for tangent on the opposite side, right, at minus x. Okay, so let me draw the angle minus x. Let me do that in red here. That's the angle minus x. All right, and well, the important feature of minus x is that the coordinates here, right, is just going to be the same coordinates as above, cosine x sine x, except it's under the y-axis, right? So this is actually going to be cosine x negative sine x, right? Because we've gone the same amount to the right, but now we've gone down as opposed to up. Okay, so I can put the dotted line like that. I can put the dotted line like that, right? And whereas before this height was sine x, now this height here is, or this position here, let me do that because it's getting a little messy, is minus sine x. Okay. All right. So what we can see is because tangent is sine over cosine, then tangent of x, let me use a different color here. Tangent of x is this number over that number, all right? Tangent of minus x, right? So this angle here is minus x. Tangent of minus x is this number over that number, right? Well, if you look at them, for the first one, tangent of x, what we get, tangent of x, is equal to sine x over cosine x, right? But if we look at the tangent of negative x down here, that's equal to minus sine x over cosine x, right? So what's the relationship between these two guys? They're negatives of each other because we've got a minus sign right there, right? And so what we conclude as, well, technically just for the region between 0 and pi over 2 versus the region between 0 and minus pi over 2 is that tangent x is equal to tangent of minus x. Sorry, minus of tangent of minus x, right? That minus sign right there. Okay, so this is for x between, sorry, let me write it like this, 0 between x between pi over 2. Okay. However, you can do this exact same analysis. Let's think about what happens between pi over 2 and pi, right? Then we would be looking at a circle, same circle. Let me just redraw it because that one's getting a little kind of messy there. Same circle. And but for angles between 0 and sorry, pi over 2 and pi, we're looking at angles that are here, right? So that angle right there. So this would be our x. Okay, what's our negative x? Well, negative x means we'd go clockwise instead of counterclockwise. The same amount though. So it would be like that. Okay, that would be minus x. And again, you see the same situation where that point compared to this point up here, their relationship is that the y-coordinate is the negative, are negatives of each other, right? So this guy up here, its coordinates are cos x, comma, sine x. The coordinates down here are cos x, comma, minus of sine x, because it's the negative of the guy up here, right? Because it's on the opposite side of the x-axis, right? Well, what is tangent of x? Tangent of x is sine over cosine, right? What is tangent of negative x? From the picture here, tangent of negative x is this guy over that. So it's minus sine x over cosine x, all right? Okay, and so what's the relationship? Again, it's the same. Tangent of x is equal to minus tangent of minus x, all right? And so again, we see that it's odd between pi over 2 and pi. And you can just keep doing this, and it's very clear that it's always going to be this relationship, and so tangent is odd. So in fact, tangent of x is always equal to, so let me emphasize always, equal to minus tangent of minus x. And so again, this relationship literally tells me is the definition of being odd. So tangent of x is odd. All right, so this helps me figure out the graph of tangent of x, because now that I know it's odd, if I figure out what it looks like to the right of the x-axis, I automatically know what it looks like to the left of the x-axis. All right, so this is one of the power, again, of kind of knowing whether a function is even or odd. All right, so that's one way to realize that tangent is odd. Let me do it a couple more ways because I think it's useful to see it from different perspectives. First of all, just maybe if you're not as comfortable with one perspective, you can maybe be more comfortable with another perspective, but also because this exercises some of our knowledge about sines and cosines. Okay, so let's look at it in a different way. Same information, we're going to figure out why tangent is odd. So let me look at the graph of sine. I'm going to put that in red. Graph of sine looks like that. Graph of sine looks like that. All right. So one thing to notice is sine is odd. We'll talk about that in a couple of minutes. All right, but in any case, sine is odd, right? Whatever value I have here, right, on the opposite side, I have the negative of that value. Okay, let me do cosine. Let me mark down the important kind of landmarks. So here is pi over 2. Here is pi. Here is 3 pi over 2. Here is 2 pi. All right. This is minus pi over 2. This is pi, minus pi, sorry, minus 3 pi over 2. And this guy is minus 2 pi. Okay. Let me mark it down like that. And like this. Okay. Cosine. That looks like this, right? And again, this is from our section on the graphs of sine and cosine. Like this, and like that. All right, and on the other side, it looks like this, looks like that, looks like that, and like that. Okay. All right, cosine is an even function. And again, we'll talk about that actually in the next aspect of why tangent is odd. So cosine is an even function. So what happens is you can kind of see that between 0 and pi over 2, what we're doing is we're dividing cosine by sine. Sine by cosine, right? So we're dividing this red portion by this blue portion right there. Okay, at any x value. So if this is my input x, I'm dividing the red by the blue. All right. Okay, now if you look at the other side, what's happening? You're dividing this guy by that guy right there, right? Now, how is that different from the picture on the right-hand side? The left-hand side here, because sine is odd, this guy here, this hump down there, is actually the same as this hump here, but negative, right? And if we think about it that way, this value here, they have the same values, except the red one should be negative. And so when I divide, I should get the same output, but negative, right? And so in that way, and you can see that the humps are exactly at the same heights, right? This guy here, sorry, I guess I shaded in the wrong two guys. This one here and that one there. So this hump here is same position. This hump here, same position. All right. So the not only is the sign swapped, but the values are always the same. We're always dividing by the same numbers. Okay. And so when you do this comparison between 0 and pi over 2 versus minus pi over 2 and 0, you can do the same comparison from pi over 2 to pi versus minus pi over 2 to minus pi, and so on. These humps, sine and cosine, are kind of made up of these humps that are always looking the same, but sometimes they're under the x-axis, sometimes they're above the x-axis, and so on. But the shape of the humps are all the same. And so that's why we get all this symmetry. All right. So this one is a little hard to see, but it kind of indicates to us that we can actually figure out whether tangent is even or odd just algebraically, right? So like I said, sine looks like this, right? We talked about this. Sine is odd, right? And again, you don't even have to know the graph. If you think about the original definition of sine, right? The same discussion that we just talked about, right? These would be positive x angles. These would be negative x angles. And the positions here, the y positions, are negatives of each other. Okay, so sine is odd. On the other hand, let me write this. Sine x is odd. Okay, on the other hand, cosine x is even. Looks like this because, well, we know that's the graph. But also, if you think about just the original definition of cosine, if I take an angle x here and I compare it with the angle negative x down there, right? What are the x values? The x values are the same, right? And the cosine is the x values. So cosine of x is the same as cosine of negative x, all right? So cosine is even, all right? And let me write down the kind of consequence of that. That means sine of x is equal to minus sine of minus x, All right. And oftentimes this one we'll write as sine of negative x equals minus sine of x. Okay. So kind of in a very, very slightly dangerous shorthand, you can think of this as you can pull the minus sign out of the sign. Okay. Very rare that you can do this. We've mentioned this before, but it does work for sine because it's an odd function. All right. Okay, what about cosine? Well, cosine is even. So what we have is that cosine of x is equal to cosine of negative x, right? They're literally equal to each other. Okay, so what about tangent? Well, tangent of x is sine of x over cosine of x, right? And the question of tangent of x, whether it's odd or even, is a question of tangent x versus tangent negative x. Are they equal to each other, or what is the relationship? And I'm claiming it's odd. So I'm trying to answer the question, are these two equal to each other with a negative sign right there? Okay, because I'm asking whether it's odd. So let me ask, is tangent odd? All right, so it's the same as answering this question, but this question is the same as answering, is sine x over cosine x equal to negative of sine of negative x over cosine of negative x, right? But we know sine of x is odd, and we know cosine of x is even. So this is going to be negative of, sine of negative x is negative of sine x, and cosine of negative x is just cosine of x because cosine is even. So what we have here is we have a minus sign there and a minus sign there. They cancel, and so we end up with sine x cos x. Is this equal to sine x over cos x? The answer is yes, right? Because they're literally the same thing on each side. Yes, so this one is yes, so that one is yes, so that one is yes, and so that one is yes. Okay, so tangent is odd. So ultimately, however you kind of want to look at it, we can figure out that the tangent function is an odd function. Okay, so we'll put that aside for a second, and let's think about the periodicity of tangent. All right, so we know sine of x has period 2 pi, so it repeats every 2 pi. We know cosine x has period 2 pi, so it repeats every 2 pi, right? So the graph of cosine and graph of sines repeat every 2 pi. What about tangent? So the deal is actually tangent does not have period 2 pi. So let's figure out, and it does have a period. It does repeat, but how often does it repeat? Or how long does it take to repeat? All right, that's the question we want to answer. And if we can answer that, putting that together with the fact that tangent is odd is going to help us get the graph really easily. Okay, so let's look at, again, because tangent is sine over cosine, let's examine sine and cosine a little closely. So sine of x looks like this, right? Actually, let me draw a little bit more. So let me draw two periods. So this is 2 pi, and there's 4 pi, right? And again, sine repeats every 2 pi. So this is sine of x. Now, what happens if we look at this guy here, sine of x plus pi? All right. So this is why, again, going to be an application of our graphing section. Sine of x plus pi, the graph of that is the same as this graph of sine of x, but we shift it over to the left by pi. All right. So up here, pi is right there, right? So we're shifting everything up here in this picture upstairs. We're shifting everything to the left by pi. Okay. So this hump, so instead of starting this hump right there, this kind of negative hump at pi, we've shifted it over by pi. So that negative hump actually starts here now. Okay. So negative hump is here, and then the positive hump would be there, and then the negative hump would be there, and so on. All right. So everything got shifted over to the left by pi. All right. Okay. Let's take a look at this. So what's the difference between the two graphs, the graph of sine of x and the graph of sine of x plus pi? Well, if I take a look at, for example, this input right there, the output is this positive number, right? If I look at the same input down here, the output is that same height except negative, right? Because again, these humps are all symmetric, right? This hump is the same as that hump, just backwards, right? This next hump is the same as the previous humps, except upside down, right? And so on. So all these kind of humps have the same shape. And so when I plug in this x right there, and I plug in the same x down here, the outputs are just negatives of each other. Okay, and you can see this everywhere along the graph. If I do the same thing, let's say just to the right of pi, right? For sine of x, the output is this negative value. But for sine of x plus pi, it's this positive value, same height except positive. All right, so the conclusion from this is that sine of x is equal to the negative of sine of pi plus x. All right, or I've written as x plus pi, so let me be consistent here. All right, and you can see this, check more points for yourself if you don't believe it, or if you're not convinced. But this is the baseline that we're going to start with in terms of sine. Now let's do the same thing for cosine. Cosine looks like this, right? It has period 2 pi, so 2 pi looks like that. And then for the next 2 pi, it just repeats. So next 2 pi, it just repeats. All right. Okay, so this is cosine of x. Now let's look at cosine of x plus pi again. Or not again, but let's look at cosine of x plus pi, right? Just as we did with cosine of x plus pi. So what's the difference between the two graphs? The difference is that the graph of cosine x plus pi is the same as the graph of cosine of x, except shifted over to the left by pi. All right. So up here, upstairs, we want to shift this graph to the left by a factor of pi, by pi. Okay. So what that means is that this point right there gets shifted all the way to the y-axis. All right. So we actually start here, right? And as we move for a distance of pi, we're going up, up, up until we get to right there. So this is traveling a distance of a horizontal distance of pi. Okay, so that means when we get to here, it's going to look like that, right? For the shift to the left. Okay, and that makes sense because upstairs at 2 pi, the output was 1. So now, because I shifted to the left by pi, at pi, the output should be 1. All right. And of course, I can just continue this. Looks like that, and then it looks like that, and then it looks like that, and so on. Okay. So this would be down here would be the graph of cosine x plus pi. Now, what's the relationship between the two graphs? Again, if I plug in a value up here for cosine, I get an output that's that high. If I plug in a value for cosine x plus pi, I get a value that's the same height except negative. Okay, and it happens everywhere. If I plug in this value right here, right next to pi, I get a negative value, right, upstairs with cosine of x. And in the same point, in the same x, I get a positive value, but the same position. All right, because again, these humps are all symmetric. And so what I conclude is that cosine of x is actually the same as minus cosine of x plus pi. Again, very similar to the sine, to the reasoning for the formula for the sine. Okay. All right, so our two conclusions at this moment are sine x is equal to minus sine of x plus pi, and cosine x is equal to minus cosine x plus pi. All right. Okay, what does this tell me about tangent? Well, tangent of x is sine of x over cosine of x. Okay. And let's look at tangent of x plus pi. That's equal to sine of x plus pi over cosine of x plus pi. But we just discovered that sine of x plus pi is the same as minus sine x. And we just discovered cosine x plus pi is minus cosine x. The two minus signs cancel, so this is equal to sine x over cosine x. What's sine x over cosine x? That's tangent x. And so what we conclude with this algebraic computation is that tangent of x plus pi is equal to tangent of x. All right, so tangent is going to repeat not every 2 pi, but rather every pi. Okay. Now, at this moment, it could repeat kind of quicker than that, but it's going to turn out that it doesn't. I don't really care at this particular moment whether it does or not, because what I'm going to do now is I'm just going to conclude from this fact that if I want to graph tangent, then all I have to do is graph it for a interval of pi, because then I just repeat that graph over and over again. All right. So what I'm going to do is I'm going to graph tangent between minus pi over 2 and pi over 2, right? That's a distance of pi. That's a distance of pi horizontally. So, and whatever I graph in this region, I'm just going to repeat the graph out here. I'm going to repeat the graph out here to the left. I'm going to repeat it again out to the right. I'm going to repeat it again out to the left, and so on. All right. So all this analysis tells me I only need to graph between minus pi over 2 and pi over 2. All right. But not only that, I know tangent is odd, right? So I don't actually have to figure out the graph between all the way between minus pi over 2 and pi over 2. I only have to figure out the graph between 0 and pi over 2, right? Because whatever that graph looks like, I'm just going to flip it upside down for the opposite side, for the minus pi over 2 to pi over 2. All right. So for example, if tangent looks like this over here, then it has to look like that over there. All right. And again, once I know this, then it has to repeat. So it's got to look like this here, and then that there, and then this here, and then that there, and so on. Okay. So all this analysis has told me that I really only need to graph tangent between 0 and pi over 2. And automatically, using the fact that tangent is odd, using the fact that tangent repeats every pi, I have the entire graph. Okay. So that's what we're going to do. I'm going to graph tangent between 0 and pi over 2. And the way I'm going to do that is I'm just going to look at sine and cosine again. So sine between 0 and pi over 2 is like this. Cosine between 0 and pi over 2 is like that. Okay, tangent is sine over cosine, right? So let's think about tangent. So add 0. So let me emphasize, tangent is sine x over cosine x. So add 0, sine x is 0, cosine x is 1, right? So tangent at 0 is 0. So I'm going to be starting here. All right. Again, I'm just graphing between 0 and pi over 2. All right. What happens as I move to the right? Well, it turns out if you kind of follow the shape of sine and cosine, is tangent is going to look like that. All right, it's going to have this kind of shape. All right. But what's really important is what goes on at pi over 2. So at pi over 2, sine of x is 1, but cosine of x is 0. And tangent is sine over cosine, which is at pi over 2, that's going to be 1 over 0. You're not allowed to divide by 0, right? So first conclusion here is that tangent has no value at pi over 2. So in terms of the graph, I should not draw anything along this dotted line because tangent has no output at pi over 2. You're not allowed to plug in pi over 2 into tangent, all right? Okay, but what happens near pi over 2? Well, near pi over 2, let's say just to the left of pi over 2, let's say I input a number there. What is sine? Sine is something very close to 1, right? What is cosine? Cosine is a number very close to 0, right? So what happens when I take a number very close to 1 and I divide it by a number very close to 0? Well, when you divide by numbers close to 0, your outputs, your result is very big, right? For example, if I divide by 0.01, right, that's the same as multiplying by 100. If I divide by 0.001, that's the same as multiplying by 1,000. So dividing by a small number gives you a big number, right? That's the short of it. And so what happens is, as I get closer and closer to pi over 2, tangent of x becomes bigger and bigger and bigger, right? So actually it looks like that. Okay, it never, it keeps going up and up and up forever as I get closer and closer and closer to pi over 2. But of course, you're not allowed to plug anything on pi over 2. So this is a vertical asymptote. All right. So this is a vertical line. So technically, I would write it as x equals pi over 2. So this is a vertical line where the function goes to infinity or minus infinity. That would also be called a vertical asymptote. As I approach that line, as I plug in inputs, right, my graph approaches this vertical line. Okay. So this is the graph of tangent between 0 and pi over 2. But as we just discussed, because tangent is odd, if it looks like this on the right of pi over 2 with a vertical asymptote here, then it's odd. So on the opposite side, it has to be the same except negative, right? So it has to look like that. So it has another vertical asymptote at minus pi over 2. Okay, but in this case, at minus pi over 2, it's diving down to negative infinity. All right. Okay, so this was using the fact that it was odd, but now using the fact that tangent repeats every pi, right? So here would be pi, here would be 3 pi over 2. I know that it has to repeat again. So I'm just going to draw this next one. Same picture, but repeat it again. All right. On the left, it would be the same picture, but repeat it again. All right, and then on the right, if I wanted to draw more, same picture, but repeat it again. Oops. Same picture, but repeat it again. Okay, so what you see is actually tangent has a whole bunch of vertical asymptotes, right? But they're all they all in a way come from the pi over 2 and the minus pi over 2 situation. You're just repeating those over and over again. Okay, so this is the graph of tangent. It's kind of terrible because it's broken and it has these kind of asymptotic behavior, which generally causes a lot of problems. Another thing to notice about sine is while tangent is that while sine and cosine, their values are always between -1 and 1, right? The graph of sine is always oscillating between -1 and 1. The graph of cosine is always oscillating between -1 and 1. Oops, sorry, that's 1. That's -1, that's cosine. This one is sine, right? Always oscillating between those two. Tangent does not, right? Tangent can have very big values. So if I asked you sine of what is equal to 10, there would be no answer, right? But tangent of what equals 10, there is an answer, right? There's in fact many, many answers because looking at the graph, right? If this height here were 10, there would be an answer there. There would be another answer there. There would be another answer there, and so on. In fact, every distance of pi, there would be another answer. Okay, so earlier I said we know tangent repeats every pi, but I said maybe the period possibly could be shorter, but it's not. We can tell from this picture. The period is actually going to be exactly pi. All right. So tangent of x has period pi, exactly pi. Okay, so it repeats every pi as opposed to every 2 pi like sine and cosine. Okay, so we figured this out kind of using a lot of the technology that we talked about, odd and even. We talked about kind of the odd and evenness of sine and cosine, right? But you can also figure out exact kind of this repeating pattern of tangent by looking at the graphs of sine and cosine together, just as we did earlier. So here's sine, right, like that. Here's cosine, like that. Right? If you analyze what goes on every 2 pi, and you kind of understand that these humps are all shaped the same, while some humps are kind of above the x-axis, some humps are below, right? If you do that analysis, kind of like what we did earlier, you can actually see this repeating pattern. You can kind of perceive the repeating pattern of tangent, right, by comparing the graphs of sine and cosine. So I'll leave that for you if you want to kind of play around with that. Okay, so this section is, we've cut it down to just the graph of tangent. Again, I don't care about the graph of cotangent because You rarely ever see it. However, the rest of this section is about modifications, right? What about the graph of tangent of whatever, 3x plus pi over 2 minus 3 times 10, right? Okay, well, I don't even have to talk about this. Why? Because you know the graph of tangent of x, right? And you know that you can get from the graph of, from tangent of x to this function that we want to know the graph of, doing the modifications that we talked about last week, right? And so if you do those modifications, right, replace x with x plus pi over 2, shifts the graph of tangent to the left by pi over 2, right? And then replace x by 3x, we'll compress it by a factor of 3. Multiply 10 to the output, we'll stretch it by a factor of 10. And then subtract 3 to the output, we'll shift everything down by 10. So in those 4 steps, you can actually graph this particular function here. Okay. You can also kind of track the points where they're going as you go from step to step. And what you'll realize is that just like with sine and cosine that we did last week, if you want to know the period of kind of this modified version of tangent, then you look at this guy here, because this guy is the one that compresses horizontally, right? So this 3x tells me that the original graph of tangent has been compressed by a factor of 3. And so the period before was pi. Now it's compressed by a factor of 3. So now the period is pi over 3. All right, so new period is pi over 3. All right, so very similar to kind of reading the period of sine of 4 pi, right? Or let's say 5 pi. The period of this guy is 2 pi over 5, right? Because it's the period of sine compressed by a factor of 5. So in the same way, the period of this guy up here is the same as the period of tangent, which is pi, compressed by a factor of 3. All right? So you can read off kind of the same information that we kind of learned in terms of the sines and cosines. For tangent, usually we don't use the term phase shift, because phase shift is most commonly used in terms of waves, describing waves, and sine and cosine describe waves, but tangent doesn't really, right? But if you were to kind of talk about the concept of phase shift, it would be in terms of, well, you would be considering, you know, this guy in here and how much you're shifting left or right. So you could do the same kind of analysis. I'm not going to do it because, again, phase shift is not a very important concept for tangent. Okay, so your homework for this section, a lot of it is graphing tangents. And again, is just an exercise in graphing any function, right? Graphing any function with the modifications that we've seen. And the kind of new thing is that we know the graph of the core foundational function of tangent now, so you can graph modifications of tangent.